Okay, so continuing on here in analysis of variance, looking at this location example, again we are comparing population means here, and so I'm going to go through here and let me see how much space I've got. Okay, I've got 2 pages, so I'm going to start here. I'm going to look at first the parameters of interest. Okay, because if in any statistics problem we need to know what is the thing or things about the population or populations that we want to say something about. And in this case we have 4 parameters, mu1, mu2, mu3, and mu4. Mu1 would be the mean selling price of all bayfront properties on Long Beach. Okay, I want you to again let it be clear that it's the mean of all, the mean selling price of all bayfront properties on Long Beach. We're going to let mu2 be the mean selling price of all, and this time bayside properties. Okay. Mu3 is the mean selling price of all oceanfront properties on Long Beach. Mu4 is the mean selling price of all oceanside properties on Long Beach. Okay, so these are our parameters of interest, and in particular the question of interest was, does the data's well, here's this expectation that different mean selling prices are what we would see for different locations. Does the data support this expectation? Okay, so we are testing that there's going to be at least one difference in the means there. So the hypotheses would look like this. So here's our hypotheses. H naught would be that the 4 population means are the same. And H1 would be that at least one population mean is different than the others. Okay, that's what we want to check. Now we're actually not checking to see which one is different, or which one might be the largest, or which one might be the smallest. That's going to be for a later discussion. But we're just saying, we're just looking to see, is at least one of them different? Okay. Step 2 here, we're going to look at our test statistic and its distribution, or we're going to state it first. Okay, we're using an F statistic here, right? And that's MSB over MSW. MSW, which follows an F distribution with numerator degrees of freedom of t minus 1. In this case, actually not t. I think we were using k, weren't we? So I'm trying to, let's see here. So k minus 1. And the numerator degrees of freedom is the total sample size minus k. I'm sorry, that's the denominator, degrees of freedom. So within our particular example, this is 4 minus 1 or 3, and this is 24 minus 4 or 20. Okay, so we're going to be dealing with an F distribution with 3 and 20 degrees of freedom. The rejection region for this distribution, recall we're going to reject if our F ratio is quote-unquote large, and so we're going to have a right-tailed rejection region. All right, so this is the F distribution here. This is going to be F sub 0.10. The upper 90th percentile of the F distributions, the F value such that the area under the curve to the right of it is 10%. Again, here the degrees of freedom in the numerator is 3. The degrees of freedom in the denominator is 20. If you look on your F table, you will see that that value is 2.38. So again, reference that from the appendix in your book. Find that critical value, that threshold, the beginning of this rejection region here. And so this here, anything to the right of that is going to be our rejection region. Okay? So moving on here to the next page, we're going to now collect our data. We would collect our data and compute our test statistic. The data has been collected and in many ways summarized. So we want to just compute our test statistic. Okay, so looking at here's our data, and here again are our summary statistics that we're going to make use of. The bayfront, bayside, oceanfront, oceanside. So when we look at this 204.5, that's going to be y1 dot bar, and say 202.333, that is y4 dot bar, and 11.1295, that is S4, the standard deviation for the fourth sample there. Okay, so we're going to make use of those in the computation of our test statistic, because first we need our between sums of squares and the within sums of squares, and then we'll take the ratio. Okay, but let's look first at our SSB here. Recall the formula for that is the sum. In this case, I would go from 1 to 4 of Ni times yi dot bar minus y dot dot bar squared. Okay, and so again, this is measuring the variability between the 4 samples or among the 4 samples. We're measuring that variability, and if it's large relative to the variability between or within the samples, then that's evidence against the null hypothesis and for the alternative hypothesis. Okay, so computing this value here, we want to first note that, well, N1, all the n's are of size 6, right? There were 6 data points in there, so I'm going to have 6 for the first term in my sum. I'm going to have 6 out here in front. The first sample mean, again, if you're referencing the table above, is 204.2 minus the grand mean. What is the grand mean? Well, that turns out to be 202.4. I'm going to square that. Let's see if we can see the 202.4 from the data there. It's not on any of the summary statistics from JUMP, but you could take all the data, add it up, divide by 24 if you wanted to, or in this case, you'd be okay in averaging the means to get the overall mean because our sample sizes are the same. But anyway, so there's a little bit of work in here, but you can verify that the grand mean is 202.4. Okay, 202.4. All right, square that. I'm going to add it now. I'm going to go from I equal to 1, I equal to 2. So I'm going to have 6 out in front again. 6 times, in this case, what's the second sample mean was 192.3 minus 202.4 squared, plus, moving on to sample 3, I'm going to have 6 out in front because N3 is 6. And the third sample mean was 210.9 minus the grand sample mean, plus 6 times 202.3 minus 202.4 squared. Okay, and so if you do the arithmetic here, add those 4 terms up, you should get something close to 1,065, rounded at 0.06. So if that's SSB, if we want MSB, you recall what that was, that's SSB over the respective degrees of freedom. In this case, it's K minus 1. So we got 1065.06 divided by 4 minus 1. You take that ratio, you get 355.02. Okay, that's MSB. That's a measure in some sense of the variability among the samples. All right, the other quantity we need for our F statistic is SSW. And you recall that one way to look at SSW was to take the sample size minus 1 times the sample variance, and you do that for every sample. So I'm going to do that up to 4. I'm sorry, this should be a 4 here. Okay. So N1 minus 1. Again here, I'm going to have 6 minus 1 times S1 squared. What is S1? Just to be clear, S1 here is going to be, or is 10.3296. All right, so I'm going to take 10.3296 square it, and then I'm going to go to the second sample here. And I'm going to have again 6 minus 1 times S2. I got to go up and look at what S2 is. 11.1295. Square that. Plus 6 minus 1 times S3. Got to look at that. 11.4091. Then lastly here, plus 6 minus 1, moving on to the fourth sample, and I got to square that standard deviation to get that S4 squared, and S4 is 11.1295. Oh, I forgot it. 11.1295. 11.1295. I do want to mention here, if you look at, we can go to the jump table, if you look at the sample standard deviations, they're all very close. I mean, they're pretty close to each other. You know, 10.3, 11.1, and so forth. And so really, thinking of this assumption for analysis of variance, what am I thinking of? This assumption here. We're pretty good with that assumption because our sample variances are so close. We could formally test for that assumption, but given the closeness of our sample variances, I'm not going to go through that process. Okay, SSW, if you add all those up, you get 2,417.5. And then MSW is going to be 2,417.5 divided by, actually, let me write out the formula for you. Recall MSW is SSW over NT minus K. Okay, so this is 2,417.5 divided by 24 minus 4. You take that ratio, you get 120.875. Okay, so now we can finally compute our test statistic. So finally, the F test statistic, F observed, MSB over MSW is 355.02 divided by 120.875. You do that and you get 2.94. Alright. So the question is that a large F value? Well, large is determined by, does it fall in the rejection region? How does it compare to other F values for that same distribution? So I'm going to go back to my rejection region here. 2.38 was considered large enough for me to reject the null hypothesis. So my test statistic of 2.94 would cause me in this next step, step 4 here, to make a decision of rejecting the null hypothesis. So here I'm going to make a decision, and I'm going to reject H naught and accept HA. Okay, my test statistic falls in the rejection region. So the interpretation here would be as follows. We have sufficient statistical evidence to conclude that location does have an effect on the mean selling price. All right. So any hunch we got from, say, this box plot that suggested the underlying population means are different is strongly supported with our hypothesis test. All right. You can do this within JMP, and JMP will do it in about 0.42 seconds. What took us 15 minutes to do, JMP will do really quickly. Here's the analysis of variance table in JMP. You can see their F ratio is slightly different there, probably due to me rounding some of the calculations beforehand. But a nice thing about JMP is that it also gives you the p-value. So the p-value there, even if we compare that to our alpha of 10%, we would still reject the null and accept the alternative hypothesis. You'll want to look at the JMP demonstration video that shows you how to do this in JMP, so that you can use it for your homework and for anything else you might need. Moving along here, this idea of data transformations. Actually, I'm gonna stop this video here. I'm gonna hit the pause button